All right, now we need to go over some basic logarithmic properties before we think about graphing them. Okay, when the base and what's inside the logarithm match, all right, we have a situation where we just get 1. So log base b of b equals 1. Why? Because that's just saying b to what power equals b. Well, clearly 1, okay? So that's just a property we need to make sure we understand. Okay? Log base b of 1 equals 0. Why? Because b to the 0 equals 1. All right, again, for either of these properties or any to come that seem completely crazy to you, convert your logarithm form to exponential form and you'll go, oh, okay, I get it now. All right, so again, it's very clear that b to the 0 equals 1 because anything to the 0 power equals 1. All right, written in logarithm form, that just means log base b of 1 equals 0. All right, so let's evaluate log base 9 of 9. Well, again, using the property we just talked about, we conclude that log base 9 of 9 is just 1. Okay? What about log base 8 of 1? Well, using the second property, we know that we're going to get 0. All right? So log of any base of 1 gives us 0. All right? Let's talk a little bit about the inverse property of logarithms. All right? So logarithmic functions are the inverses of exponential functions. Remember, that means domain and range flip. That means we flip over the red diagonal we see, y equals x. Okay? And they undo each other from an algebraic standpoint. Okay? So here, if I have log base b of b to the x, well, this part here, the log base b of b, cancels because they're inverses, and we simply get the power, which is x. Here, if we have b raised to the log base b of x, then again, the b raised to the log base b cancels because they're inverses, and we simply get the x, or I will often say the x falls out. Okay, and we can see our inverse property here. Our y-intercept here at 1 becomes our x-intercept. All right, our horizontal asymptote for exponentials becomes a vertical asymptote for logarithmics. All right, let's use the inverse property. Log base 7 of 7 to the 8. Well, the log base 7 of 7 undo each other, and we get the power on the 7, which is just 8. All right, similarly here we have 3 raised to the log base 3 of 17. Well, the 3 raised to the log base 3 undo each other, and we simply get 17 as our answer. All right, let's talk about a couple of common logarithms. The logarithmic function with base 10 is called the common logarithmic function. If you look on your calculator and see a log button, L-O-G, that means log base 10. We typically, when we see a log without the base written, as we see here, we just commonly understand that to be base 10. Okay, and so let's actually do a little word problem here. The percentage of adult height attained by a boy who is X years old can be modeled by this logarithmic function, 29 plus 48.8 times the logarithm of x plus 1, where x represents the boy's age from 5 to 15. All right, so, and f of x represents the percentage of his adult height. Approximately what percentage of his adult height has the boy attained by age 10? All right, well, what does this mean in terms of math? Guys, it means to plug in 10 for x, okay? The first thing we do is parentheses. We add 10 and 1, okay? Then we're going to actually get log of 11 in our calculator, and if you're following along with your calculator and do log of 11, we get 1.04139 and more decimals. We're going to take that, multiply it by 48.8, and get something around 50.82, and we're going to add that to 29, and we get just about 80%. I get 79.82. We can round that up to roughly 80%. So this 10-year-old boy has attained approximately 80% of his adult height by age 10. Okay, so properties of common logarithms, I always like to give you guys kind of summary charts. We have our general properties here, and then I also give it to you here with log base 10, or the common log. All right, just make sure you're paying attention to the two inverse properties, all right, the one property and the base to the one power property. All right, now let's talk about the other common logarithm called the natural logarithm. All right, it's the inverse of the natural exponential function, or base e. All right, so if we invert e to the x, we're going to get ln x. Okay, ln is the abbreviation for the natural log function, and on your calculator you will see an ln button. Okay, all right. So again, we have our properties of the natural logarithms. I'm going through them. Ln of 1 is 0. Ln of e is simply 1. And then our inverse properties, where we just get the x to fall out, as I will often say. All right, but let's do an application. When the outside air temperature is anywhere from 72 to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The function f of x equals 13.4 times ln of x minus 11.6 models the temperature increase f of x in degrees Fahrenheit after x minutes. Use the function to find the temperature increase to the nearest degree after 30 minutes. All right, well, what does that mean we need to do? That means we're plugging in 30 for x. All right, again, if you're following along with your calculator, the first thing I'm going to do is get ln of 30. I use my ln button, I type 30, and I get 3.4012. I'm going to multiply that with 13.4 to get 45.576. And lastly, I subtract 11.6 to get 33.976, or roughly 34. All right, so the temperature will increase by approximately 34 degrees after 30 minutes. This is the main reason why we don't leave dogs or cats or babies in a closed car when it's hot outside.